Today we shall discuss about a new topic, that is influence line diagram or ILD. So first of all, take an example of beam. Say this is a beam, a simply supported beam here, and it is subjected to simply a point load at this point, say W, okay, at the midpoint, and the length is L. So if I want to know the bending moment diagram or shear force diagram, you can easily calculate. So first of all, we have to calculate the vertical reaction, that will be W by 2. So if you calculate the shear force and if you draw the shear force diagram, say this will be the shear force diagram for this particular beam. And if you draw the bending moment diagram, so this will be the bending moment diagram, okay. So the maximum value of the bending moment will be W by 2 multiplied by L by 2. So WL by 4. And the maximum value of shear force would be W by 2. This is positive shear force and this is negative shear force. Now the question is that, suppose we have a particular section at this point. So this is the continuation of this section. Now the question is that, what will be the shear force value for this particular section and for this position of load? The answer will be this value. This amount of shear force will be created at this particular section of this beam due to the application of load W at the midpoint. And what is the bending moment value for this section, at this section, for the load W at midpoint? This is the bending moment value, and you can easily calculate that. So this value is W by 2 and this value you can calculate. You have to know the distance. Once you know the distance, this distance from any end point, you can easily calculate. So you can see our load position is fixed. This is the point of application of load, and I draw one section and I can get the bending moment value or shear force value from this diagram. If I consider the section at different place, suppose this is the another place. So if I want to know the amount of shear force created at this point, amount of shear force produced at this point, at this section of the beam, then we have to simply go through this diagram, and this height represents the value of the diagram value of the shear force at this particular section, or if you want to know what will be the bending moment value at this particular section due to the application of W load at this midpoint, then you just go through the diagram, and this particular distance, will indicate the amount or this value of this distance will indicate the bending moment value at this particular section. Okay, or if you draw the section at this point, then what will be the amount of shear force? This will be the amount of shear force, and what will be the amount of bending moment? So this will be the amount of bending moment. So you can easily understand one thing, that our load position is fixed at the midpoint, and we can vary the section from 0 to L. So this is the distance, or this is the length of the beam. Okay, now we just start from this point. Say this is A and this is B. So you just start from this point to this point, and you can vary the length of the position of the section from point A. When the section position is suppose this is x. So when x is equal to 0, that means the section lies at this point. Okay. When the x is equal to L by 4, the section lies at particular this point. Okay. When the x value is L by 2, then the position of the section is this. When the x value is L, then position of the section is this. Okay, so you can understand that the section is moving here. We can vary the position of the section and we can get different value of the shear force and bending moment diagram for this particular application of load W at the midpoint. The position of load is fixed, and position of load is not fixed. Okay. Now for the inference line diagram, the case is totally opposite. So suppose this is the beam. So this is simply supported beam. Now we have a particular section. So say maybe this is the particular section. Okay, section is fixed at this point, and the load is moving. So it may be at this point load, W load. It may be at this point. It may be at this point, or at this point, or at this point, or at this point. Whatever it is, the load is moving. Okay. Now we have to find out. So reaction number 1. Reaction, or you have to find out say shear force, or you have to find out the bending moment, or maybe you have to find out the axial force. Okay, so all those are basically for beam, and this is basically for truss. So you have to find out the reaction or shear force or bending moment or axial force or whatever it is at this particular section, and you have to calculate the maximum shear force. We have to calculate the maximum bending moment or maximum axial force for the application of load. So actually you have to find out the position of the load. Okay, so for which position of the application of load, the section at this section the shear force or bending moment or reaction will be the maximum. Okay, so this is the things we have done in the influence line diagram. So with the help of influence line diagram, basically we calculate the reaction or shear force or bending moment or axial force for a particular section for different position of the load. Okay, or you have to you need to find out the a specific position of the load for which the shear force or bending moment will be maximum for this particular section. Okay, so obviously there is also a diagram also. Influence line diagram means there is some diagram. Okay, so you have to draw the diagram. Say this is the beam and this is the section, and so you just draw any diagram with the help of, say, this is the diagram. Okay, with the help of this diagram you have to find out the shear force or bending moment value or reaction for any reaction or axial force for truss. You have to find out. So basically this diagram represents this diagram. We say this is the diagram for shear force. This is the diagram for shear force. It is not indicating the value of the shear force for infinite number of sections. Please keep in mind, it is not indicating the value of the shear force for infinite number of sections. It is basically represent that the shear value of the shear force for specific section, for the particular section. Okay, for the first case we can see there is a number of section. We can divide, we can get infinite number of section for this case. Okay, there is infinite number of section, but for influence line diagram we have a particular one section only, particular one section. So we have to find out the value of the stress diagram, stress resultant, value of the stress resultant, that is shear force, bending moment or axial force, etc. for particular section. So suppose this is the diagram for shear force. So we have to write this is the ILD for shear force. This is the ILD for shear force only. Okay, and this is also for a particular this section. Okay, suppose you have the another section. Suppose for the same problem, you have the another section. The section is at this position. Okay, section is at this position. Now the diagram is not exactly the same for the with the previous one. Diagram will be the different. So this is the diagram maybe. Okay, so these two diagrams are totally different. Okay, this diagram indicates only the amount of shear force for this particular section, and this diagram will indicate the amount of shear force for this particular section. Okay, so like that we have another diagram for bending moment. So this is influence line diagram for bending moment. Okay, and for this particular another section we have another diagram, another influence line diagram for particular for bending moment for this particular section. Okay, so this bending moment diagram and this bending moment diagram will not be equal. Okay, this shear force diagram and this shear force diagram will not be equal because we have the different position of the section. For this case, this is the position of the section. Suppose this is the x. So from point A, the position of the section is distance x from the point A, and for this case, say this is the x. Okay, so for this case, the position of the section is x distance from point A. For this case, the position of the section is x1 distance from the point A. So this is totally different. Now, the simple things is that for the stress resultant or reaction, say this is the simply supported beam and this is the particular section, and we have to draw bending moment or shear force or in a reaction, however it is. So suppose this is the diagram for shear force. I will be for shear force, and this is the diagram ILD for bending moment, or say this is the diagram ILD for reaction A, or this is the another diagram. So this is ILD for reaction B. Okay, so there are four different figures are there. So now one thing is that the formula for ILD is the same for different stress resultant. Okay, so for shear force the formula is same, for bending moment the formula is same. Okay, the formula is like that. Suppose we have the load at this position, say W. Okay, we have the load at this position. So draw a vertical line through this load, and you have to calculate the height. So suppose this is the height x1, and you have calculated this is x2, this height is x3, and this height is x4. So the four diagrams are totally different. That's why we will get four type of height at this same position. Okay, at the same position we will get four different kind of height because the diagrams are totally different. So the formula is like that. If you want to know the shear force at this position for this particular load, for this particular position, the shear force value will be W into x1. Okay, and for the bending moment at this position, for this particular position of the load W, the bending moment will be W into x2, and for the reaction, if you want to know the reaction RA, for this position of the load W, then the formula is same, W multiplied by this height. Okay, and for reaction RB, the formula is same, W multiplied by the height. So the formula is the general formula is like that: load multiplied by general formula. Okay. So load is fixed. For all case you can see load is W. Okay. But the height is changed. When the shear force value you are calculating, the height is x1. When you are calculating the bending moment, the height is x2. When you are calculating the reaction RA, the height is x3. And when the reaction is RB, then height is x4. So for different kind of height, you will get the different result. Okay. So these things you have to keep in mind. Now suppose you have a simply supported beam and you have a load W at this position. So this distance is A and this distance is B. So total length is L. Now what will be the reaction? Let us try to calculate the reaction. Summation of vertical equals to 0. So VA plus VB minus W equals to 0. This is one equation. And another equation is summation of moment equals to 0. So taking moment about point say B. So VA into L minus W into B equals to 0. This is another equation. So we can say VA into L equals WB and VA equals WB by L. So if you put VA value in the equation 1, you will get VB. So VB equals W minus WB by L. So this is L. So L minus W, L minus B into W, or W A by L. Now our concern we are concerned about VA only, like that, because we are going to create the influence line diagram for reaction VA. So reaction at point A or VA, whatever it is, equals W B by L. You can see W multiplied by B by L. Okay, this is W multiplied by B by L, or we can write this is actually W multiplied by L minus A divided by L. Now you have to draw the influence line diagram. So in the previous slide I have shown to you that the general formula is load multiplied by height. Okay. So obviously this is the load and this is the equation of height, nothing else. Okay. So when A equals 0, minus A by L equals 1, and when A equals L, then L minus A by L equals 0. So you can easily draw this diagram. So this is the length of the beam, and when A equals 0, so A equals 0 means the position is this position. At this point A equals 0. Okay, we are counting the A distance from here. So when A equals 0, this height will be 1. So this is the height and this height is 1. And when A equals L, that means this position, the point B. At point B, this height is 0. So now draw the straight line. So this diagram will indicate the influence line diagram for RA. Okay, this diagram is this influence line diagram is for reaction RA. Now this is the simply supported beam, and we have a particular load at this point W, and this is A and this is B. Now the influence line diagram for reaction is this. This is 1, this value is 1, this value is 0. Now what we have to do? We have to draw a line here, a vertical line. So this distance you have to calculate. Suppose this is x. Now how we can calculate this distance x? You can see this distance is b and this distance is L. So from graphical representation we can write 1 divided by L equals x divided by b. Okay, because we have the same angle for two different triangle. We have two different triangle. This is one triangle, and this is another triangle. So for two different triangle we have same angle, that's why we can say y by x, that is 1 by L for first triangle, equals y by x, that is x by b for second triangle. Now you can calculate x, that is equals to b by L. Now you just use the general formula for reaction RA equals load multiplied by height. Load is W and the height is B by L. So the reaction value will be WB by L. Okay. So this diagram is the influence line diagram for RA, reaction RA. Now for the same case, if you want to know the influence line diagram for RB, the reaction B, so you can calculate or you can draw using this method that I have already shown to you, and you can find the diagram will be like this. And this value is 1. So this is the influence line diagram for RB. Now draw a vertical line here, and you need to calculate this distance. Say this is x1. So we have two triangles. This is the first triangle, here we have the vertical height is 1 and the horizontal distance of the triangle is L. And we have the second triangle, that is this one, where the vertical height is x1 that we have to calculate, and the horizontal distance is A. So from the similar triangle, similar angle triangle, so we can say that 1 by L equals x1 by A. So x1 equals A by L. Now value of RB will be load into height. So load is W and height is A by L. So this is W A by L. So this is the answer. So in the next class we will discuss how can we draw the influence line diagram for shear force, and also we have to know this is the application of point load, and we will learn how we can draw the influence line diagram for UDL also. That we will learn all those things in the next class.